Hi, welcome to our new little mini unit on limits. We're now getting into the official calculus content. So that's exciting stuff. So what is a limit? A limit tells us what should happen with a function. Not necessarily what does happen, but what should happen. What value are we approaching? Allow me to explain. Limits tell us which value, and that is a y value in particular, an output, the function is approaching. Keyword there, and in particular, that is a y value. This is as x approaches a particular x value. We would write it like this. The limit as x approaches a, so that a is a particular x value, the limit as x approaches a of f of x, your function, equals this L. This is the number that you are approaching. So the idea is the output gets close to L. And here's an important thing to note. What quote unquote should happen with a function, that is the limit, that may not necessarily be what does happen. So I mean the particular function value itself. Allow me to illustrate with an example. And here we're getting into what's called a piecewise function, where you define the function in, well, multiple pieces. So f of x behaves just like the function f of x equals x when x is anything but 1. But when x is equal to 1, we say that it's 0. Let's take a look at the graph. Okay. So almost everywhere except when x is 1, this is just the line y equals x. But we have to draw a hole here because the function behaves differently when x is 1. You drop down to the y value of 0. So let's take a look at the limit as x approaches 1. So as our x gets close to the x value of 1 for this function, which y value are we approaching? Well, we're approaching here, right? As we get very close to 1 in our x value, our line is going up, up, up. Oops. Up right to that hole. And likewise, if we approach from over here, we're approaching this height of 1. So that's what the limit is. This is the height that we're approaching. Now, is this actually f of 1? And the answer is no. Even though we're approaching this height of 1, we're actually down here. That's the actual function value. So this is what I meant when I said what should happen, the y value that we're approaching, may not necessarily be what does happen. You can have a sudden jump downward like this. But that's not what a limit is concerned with. A limit is concerned with which value am I approaching. Let's talk one-sided limits. We care about which direction we're approaching our x value from. So if we're approaching this x value a from the right side, and if that's all that we're concerned with, then we have a special notation for that. The limit as x approaches a, and then this plus superscript. So that plus means we're talking about one particular direction. So what's happening as we approach from the right side? So if this is a, and just here's a rough function, then this one-sided limit is asking what happens as I approach a from the right side. Likewise, if we're approaching a from the left, and if that's the only direction I care about, then you write it like this, with this minus superscript. So let's see an example where this really shines. Another piecewise, these are good for limits. Let's say it looks like the graph y equals x squared when x is less than or equal to 2. But then it looks like the line y equals negative x plus 4 when x is greater than 2. So this is a bit of a Frankenstein mishmash, if you will. Let's graph that. So here's a height of 4, 3, 2, 1. Try going out to 4 maybe. Yeah. 1 second. All right. Here's 2. And we'll want to go to the left a little bit. All right, so when x is less than or equal to 2, this is going to look like the parabola. So we have a height of 4 at negative 2, height of 1 at negative 1, 0, 0, 1, 1. And then we have the point 2, 4. Okay, connect. That doesn't look amazing, but it'll do. So we do have to stop suddenly here when x is 2, because this is a piecewise function and there's a sudden shift when x is 2. Okay, now it looks like the line negative x plus 4. So y-intercept of 4, we're not going to draw it because we're not over there with this line. Again, x is greater than 2 here. But it can give us a sense of where we end up. If I have a slope of negative 1, keep going down 1 over 1 until we hit right here. 2, 2 is a point on that line. I'm going to draw it as a whole because this is when x is strictly greater than 2. So not equals, that's taken care of over here. So I have to draw an empty hole, but then we can continue the line downward from there. And we have an x-intercept right about there. That doesn't look too good. Okay, close enough. So this is a graph of the piecewise function. And now the purpose of what I just did is to highlight one-sided limits. We can write it over here on the left. The limit as x approaches 2 from the right of f of x. This is a one-sided limit from the right, this plus. So that means all I care about is as I'm approaching 2 from the positive side. So that means what's happening with this line? What height am I approaching? Well, I'm approaching this height of 2. As we approach from the right side. But on the flip side, if we're approaching the x value of 2 from the left, that means from the lower side, well then what's happening with the function is it's following this parabola. And then we're headed towards the height 4. So that's on the left side. Notice that these one-sided limits are completely different. That's due to this piecewise nature. And while we're at it, what is f of 2 itself? Well, that would be this filled in point here, 4. Whoops. All right. So, to have a full limit, which we would normally just say a limit, full limits must be two-sided. That's important. So if I just talk about a limit, generally speaking, and I don't specify a side, like left or right, then we're talking about a two-sided limit, both directions. In other words, when I write the limit as x approaches a of f of x, so no one-sided business, we say that this exists if and only if these one-sided limits agree. So for just a regular plain old limit to exist, you have to get the same thing whether you come in from the right or from the left. So no sudden jump like we had in the previous example. So quick word on that. In the above example, we would have to say that the limit as x approaches 2 of f of x does not exist because it did not agree coming in from the left versus the right. If we look at that for a second. Right, coming in from the left, we have a height of 4. Coming in from the right, we have a height of 2. Because of that difference, there is no plain old limit as x approaches 2. Now, what if we do not have a graph? Couple strategies. When calculating a limit without a graph, wow, that looks bad. Here's the first thing you should try. Try just plugging in the value first. Plug in x equals a into your expression. Now, admittedly, most of the time this will not work, but sometimes it does, and this is the best case scenario. So you do want to try this first. If it doesn't work, so otherwise, whoops, we'll probably use some sort of algebra trick. Some sort of manipulation to make the expression work. So some examples without looking at a graph. Call this part A. The limit as x approaches 3 of x squared. Well, try plugging in 3 for x into this expression, and that works just fine. It works like you would want it to. You're just approaching the y value of 9. Nothing funny going on with this function. It's very well behaved. Part B. The limit as x approaches 7 of 2. Now, what do we do here? I want to plug in 7 for x. Technically, you can do that. It's just that nothing happens. This is just the expression 2 everywhere. It's just 2. It doesn't even depend on x at all. So x approaching 7 is somewhat irrelevant. Think of this as the horizontal line, y equals 2. It's just flat horizontal line. No matter which x values you're approaching, you're always going towards the same height, that flat height of 2. Now here's where it gets a little more interesting. For one thing, it doesn't have to be the letter x. That's typically what we use, but could be something else. I'm using b in this example. So as b approaches -2, let's look at this rational expression. I would begin by trying to plug in -2, but you're going to run into a problem pretty quickly. It turns out you get 0 over 0, which it's called an indeterminate form. Basically, there's nothing you can do with it. So this does not work. You're especially dividing by 0. You'll find that you get a 0 over 0 form, which is not something that you can work with. So as I mentioned, if plugging in does not work, then we'll want to use some sort of algebra trick. And the trick in this case is factoring. In particular, factoring the numerator and this will work. Now that we've factored, we're in a position to cancel. And now -2 is not a problem point. Because the b plus 2's canceled, we're left with b minus 1, and we're free to just plug in -2 for b. And this tells you which y value the function is approaching. So if you were to graph the original function, like suppose the b's were x's, they serve the same role. If you were to graph this, technically you would have a hole when x or b is -2 because of this dividing. But even though you have a hole, you're still approaching this value. When it comes to the limit, that's all that matters. What are you approaching? And by the way, this is good etiquette. Teaching a good etiquette here. For every step, until the very end, I keep writing my limits. This limit is not equal to just this expression, but rather the entire limit of this expression. So we're writing our limits at every step till we get to our final evaluation. Now let's discuss properties. Suppose we know two limits, different functions, but approaching the same x value of a. If the limit as x approaches a of the function f of x is equal to L, and the limit as x approaches a of g of x, let's say, is m, Then we experience the following properties. First, the limit as x approaches a of this mixture. So leave a little space. You can add the functions together. And even more than that, you can multiply them by certain numbers. So c is a real number, and d is a real number. When you bring them together like this new limit behaves very nicely. It's just that number c times f's individual limit of L plus d times g's individual limit. So limits respect addition, and we would call this scalar multiplication, multiplying by a real number. So this is technically called the linear property, linearity. So you can take the limit of a sum of two functions and even throw in some real numbers, and the limits would behave just like you would want them to. Next property. What if I take the product of those two functions, f times g, and take the limit towards that same x value, a? Then this also works like you would expect it to. Just take the product of their individual limits. So limits also work very well with respect to multiplication. Now, likewise with division, but with one little caveat. This only works if m is non-zero. And then if I divide these two functions and take the limit, then the result is just the quotient of their individual limits. Again, you just need m to not be 0, otherwise this doesn't work. You'd be dividing by 0. Next, sort of a 2-for-1. Going to introduce this little n. If n is a positive whole number, so for example, 1, 2, 3, 4, 5, 6, etc., then we get the following property. The limit works really well with respect to exponents. So if I take that function to the n power, take the limit, then the result is the original result, L taken to the n power. So it works like you would want it to. And then similar result for a radical, the nth root. The result is the nth root of L. So you have all of these very nice properties with limits. They behave just like you would want them to when you're adding functions, multiplying them by a real number, multiplying the functions, dividing the functions, or taking the functions to a certain power, or the nth root. These all behave very well with limits. And okay, we'll be a bit technical here. You just need to add something which guarantees that this thing exists in the first place. This is assuming that f of x is not negative around this x value a when n is even. I wouldn't worry about this too much, but I do technically need to say this. This just ensures that this expression exists in the first place. Remember, you're not allowed to take the square root of a negative number. That's basically what's going on here. Let's do some more limits. Part A. We'll use the letter y this time. Let's try plugging in this value for y. Well, notice that we'll get 0 on the top, but the denominator is actually totally fine. 0 over 1, this is okay. The result is just 0. It's when you get 0 over 0 that you run into problems. Part B. Let's say we don't know too much about these two functions f and g, but we know that the limit as x approaches 5 of f of x is 6, and the limit as x approaches 5 of g of x is negative 7. Then I can figure out the limit of their sum, and I'll throw in an extra times 2 for good measure. This is that first linear property I was talking about. Well, we know that the limit as x approaches 5 of f of x is 6. So 6 plus, now we've got a times 2. And g's limit is negative 7. So it works just like you would want it to. And this is the result. Now, this is a fun one. I'm just going to use y again. Why not? Oh, excuse me. Y minus 1. Notice that if you try to plug in 1, you're going to run into some problems right away. You'll get a 0 over 0. So just plugging in 1 doesn't work. That means we'll want to do some sort of algebra trick to rearrange this so that we can make it work. And the trick, if you have rational, that's division, involving square roots, then this is probably going to be multiplying by the conjugate type of problem. So in particular, this is the part which involves the square root. So we multiply by its conjugate, which is just flipping the sign. But if you're going to multiply one part by this new thing, I have to do it to both the numerator and denominator. Keeps things equal. But now that we've done this, this will eliminate the square root. which means we'll probably be in a better position. But let's see what happens. So I multiply by the conjugate, and the numerator will become y. Then the outer plus inner parts of the FOIL will cancel by design. Right? We'll have a square root of y and then a minus root y. And then for the last part of the FOIL, we have a minus 1. Okay, repeat the denominator. Notice that I can cancel this with the y minus 1 below. So 1 over square root of y plus 1. Notice that now if I plug in 1 for y, this is totally fine. And the answer is just 1/2. So we multiplied by the conjugate in order to rearrange things. That allowed us to do some canceling. And then it was actually possible to just plug in 1 for y. So the answer is 1/2. Now let's discuss limits involving infinity. Very important. This could be positive infinity, could be minus infinity, and we'll talk about it in terms of x and y. Let's take a look at the function f of x equals 1 over x, or y equals 1 over x. Let's draw a graph. So if you want, you could plug in some x values and try to make the shape from there. I won't spend too much time doing that. But if I plug in 1 for x, then I get 1 over 1. So height 1. If I plug in 2 for x, then the y value is 1 over 2, 1/2. So we're down here. If I plug in 3, I get 1/3. And notice if I plug in, say, 1/2 for x, 1 over 1/2, that flips to 2. So we have a height of 2. So what will happen is that as we move out, we'll get very close to 0. And as we get close to the y-axis, we just shoot up forever. So what I just described is a one-sided limit. As our x value approaches 0 from the right, so as we're headed towards 0 from the right side, our graph is just shooting up towards infinity. Remember, we cannot plug in 0 for x, so as you plug in smaller x values, our graph will just rise higher, 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 higher. So this right-sided limit as x approaches 0 of 1 over x is positive infinity because we keep rising higher and higher to no end. Now, what about the left one-sided limit? Well, I haven't quite drawn that yet. Let's think about it. So, if I plug in -1 for x, then my y value will be 1 over -1 or -1. So we've got a point here. And let's say I plug in -2, that's -1/2 as a y value. Now, what if I plug in -1/2 for x? The result will be -2 for y. So we have a similar looking curve. So there's a nice symmetry to this graph. Now, as we approach x equals 0 from the left side, notice my graph is shooting down towards -infinity. We go down to ever increasing negatives. So those are some pretty different one-sided limits. And by the way, when the result is infinite or negative infinite, that means technically the limit does not exist. We say that these limits don't exist because it's not a particular real number, just this unboundedness. But this is still some information, right? Positive infinity versus negative infinity. So there's still a distinction there, but we would say technically these don't exist because they're not real numbers. So I did talk about this a bit already, but you're allowed to talk about infinity with the x's. So as x approaches infinity, that means as I move out to the right forever, notice that we actually are approaching a y value. This is what's called a horizontal asymptote. This horizontal line, the x-axis, which we get closer and closer and closer to, but never quite touch. The limit as x goes to infinity of 1 over x. So what happens to this y value as I plug in larger and larger and larger numbers for x? Like say 1 over a million, x being 1 million, that is. Well, our graph is headed towards 0. 1 over a million is a very, very small number, close to 0. So if I move this here for a second, as we keep plugging in larger and larger x values, our graph gets very, very close to the x-axis at height 0 without quite reaching it. So that's a limit. We're approaching height 0. And we can talk about negative infinity. For x, that just means we're moving to the left. So that would be this part over here. If I just keep moving further and further to the left, similarly, you're going to approach the x-axis, height 0, but you'll never quite reach it. So the limit as x approaches -infinity of 1 over x, that's also 0. We're just approaching it from two different sides, but that doesn't really matter. Both approaching height 0. So this goes to show if I have a finite number and I'm dividing by something that's blowing up, So in this case, I have just this fixed finite number 1 divided by something that's blowing up. And this could be plus or minus infinity. This will always go to 0. Again, if the top is some finite number. If you have infinity over infinity, that's a much more complicated situation. Which leads us to the next example. Two parts. So the limit as x approaches infinity, as my graph moves further and further to the right forever, which y value are we approaching, if any at all? And the function is x cubed plus 2x minus 1 all over x minus 1. So notice if you try to plug in infinity, if you will, technically not a real number, but if you plug in very large numbers, you'll see that we're essentially getting infinity over infinity. And that is pretty complicated, doesn't really tell you a whole lot. So instead, what we have to do is a little manipulation. The trick is to find the highest power of x that you can in this whole thing, so x cubed, and then you divide everything by that. So I'm multiplying the entire numerator by 1 over x cubed, and you have to do the same thing below. So again, this was finding the highest power of x that we could find, and we're dividing it off. Again, good etiquette, keep writing your limits until the end of the problem. So by multiplying by 1 over x cubed, that's distributing onto every single term. So every term is being divided by x cubed. Same thing with the denominator. And now you'll get a lot of canceling. X cubed over x cubed becomes 1. We have some x's canceling, 2 over x squared. And then this remains the same, 1 over x cubed. We have a 1 over x squared that reduces, minus 1 over x cubed. Now you may be thinking, hold on, this looks very complicated. But this is actually much better suited for plugging in large x. Because remember, finite number divided by something that's growing towards infinity, it means that part is headed to 0. So I'm going to be a little careful here. I'm not going to write an equal sign exactly. And this is a little nitpicky. But that's because this is technically not a real number. You could say equal, that would be fine. Don't worry about it too much. Notice, this actually does give us an answer because I have a finite number, or excuse me, I should say non-zero divided by 0. I haven't quite spelled this out yet, but if you have something non-zero divided by something going to 0, then this will go to one of the infinities, either positive or negative. You would have to look a little more closely to determine which one. But for our purposes, we'll just say it does not exist. So this is the type of wording you'll see in Pearson. This does not exist, and is either positive infinity or negative infinity. So this is a little rule of thumb here. If the top were 0, like a 0 over 0 situation, that is not really something you can work with. It doesn't tell you a whole lot. But if we know we have something non-zero, like 1 in this case, we're going to 1 in the numerator, but the bottom is becoming nothing. Well, 1 divided by very small numbers makes you blow up. Last one. The limit as x approaches infinity of 2x squared minus x minus 4 over x squared plus 1. Well, again, if you plug in very large numbers, then you get infinity over infinity, which doesn't tell you a whole lot. So again, you want to find the highest power of x that you can, in this case x squared, and divide everything by that. Now I'm going to show a little less work this time. This will cancel to 2 minus 1 over x minus 4 over x squared. 1 plus 1 over x squared. So now what happens when I plug in very large x? This will head towards 2 minus 0 minus 0. Right, these parts will become 0 over 1 plus 0. And this is totally tame. Just 2 over 1. So there's a clear answer of 2. All right, next time we will discuss continuity of functions, and that's closely tied to the limit. See you then.